This is review video 43, how to predict the direction reactions will proceed toward equilibrium. So as a reminder, reversible reactions, and you know it's a reversible reaction because we can see that double-pronged arrow, they are going to proceed both forward to produce products and backward to produce reactants until our rate of our forward reaction equals the rate of our reverse reaction. And once that happens, we reach a state of equilibrium. We have two different values that we can look at to see what the properties are of these reactions as they approach equilibrium and when they are at equilibrium. So we can look at Q values, which are a reaction quotient value. And as a reminder, those reaction quotients are taken when a reaction is not yet at equilibrium. And we do that by looking at the ratio of products to reactants, so products divided by reactants, and those are raised to the power of their coefficients in the balanced chemical equation. When a reaction is at equilibrium, we look at a K value, which is the same thing. Again, we have our products divided by our reactants raised to the power of their coefficients. Now, in terms of Q and K, what they mean is different depending on their value. So when Q and K values are large, it means that at that moment, there are a lot more products, right? Because we know that Q and K values are products divided by reactants. Therefore, if it's a big value, it means you have a large numerator, meaning you have more products. So visually speaking, if I had this reaction here, reactant A is being consumed and turning into reactant B, and I had a large K value, that means that at equilibrium, we're going to have mostly product because that is a large value, meaning that the numerator in the K expression would be large and we'd have a lot of B, and you can see that in the little box there. Conversely, when our Q values and our K values are small, it means that there's more reactants at that moment in time. So again, looking at this same reaction, let's say its K value was really little, 5 times 10 to the negative fifth. That means that at equilibrium, we do not have a lot of products and we mostly have reactants. So we can again see that visually down below. The same could be said for Q values. If this reaction had a Q value of 1 times 10 to the negative fifth, that means that at that moment in time, there happened to be a lot of reactants present. It just isn't at equilibrium. But again, it doesn't really matter. It's at that moment in time. In terms of comparing Q and K values, that's how we can predict the direction that reactions will go towards equilibrium. And we can do that because we know that over time, a reversible reaction, when left alone, will establish equilibrium eventually, which means that it's constantly going to be moving towards equilibrium. So if we measure the concentration of products and the concentration of reactants over time, we will see that Q values will slowly start to become closer to K over time. So let's say that, again, we have that same reaction, A and B, and it has a K value of, let's say, 10 to the negative fifth over time, right? What that means is if I measure products and reactants over time, slowly, we'll get closer to this number as we approach equilibrium. So by comparing a Q value and a K value, I can see, hey, does my reaction need to go forward to reach equilibrium or does it need to go backwards? So if Q is greater than K, what that means is there are currently too many products and the reaction has to proceed backwards to reach equilibrium. So visually, let's look at what that means. We have this same exact reaction, A to B, and its K value is small. At a specific moment in time, before that reaction has reached equilibrium, its Q value is 2 times 10 to the third. So we're seeing that Q is greater than K in this point. That means that at whatever time Q was measured, we currently have a lot of products. How do I know that? Because Q is a big number. That number means we have a lot of products. But at equilibrium, where this reaction is moving, K is small, which means that at equilibrium, we do not have a lot of products and we have mostly reactants. So as this reaction moves toward a state of equilibrium, we need to somehow generate more reactants. And the way to do that, according to this equilibrium system, is to go backwards, is to follow that left arrow. Because I know that the reaction is heading towards equilibrium. And if equilibrium is that there's a lot of reactants present because of this small k value, that means I need to go backward to get there if this is where I am starting. Okay? If I have the opposite situation, if Q is smaller than K, then it means the opposite. That means that there are too many reactants and the reaction will proceed forward toward equilibrium. So again, let's visually look at that. This time, I'm looking at a Q value of 2 times 10 to the negative third, meaning, of course, that that Q value is small. So currently, I have a lot of reactants present, but we know that that reaction is going to proceed towards equilibrium, and its equilibrium state has a high K value, meaning that there's a lot of products present at equilibrium. The way to get product is to go to the right. So my reaction will proceed to the right towards equilibrium because Q happens to be smaller than K at this moment in time. All right? This specific topic I find is hard for some people to really comprehend. So to be perfectly honest with you, if you come across this question and you can't really conceptualize Q and K, draw it out. Draw it out just like we did here. Because for me, visually, it's easier to imagine what's happening if I can see it. So if you have issues with that, you don't understand how these things are moving, what it means for Q to be smaller or larger than K, you need to come talk to me and we need to practice drawing it out a few times. So again, please come talk to me if you have questions.